Hey, my name is Jordan Deshawn, and this video is about Step 3, hydraulic design, in the new Pumped Safe Water design tool. Here in Step 3A, we're going to define the design flow rate. And if you remember, this yellow icon is here to help you get to an optional calculator. So you can click this blue link and it'll take you automatically there, where you can define the daily water demand and the estimated hours of operation per day, and the tool then automatically calculates the design flow rate estimated based on these two inputs. In this case, it's 6.7 meters cubed per hour. So jumping back to step 3, we can see the design engineer for this project entered a flow rate of 7 cubic meters per hour, which is slightly higher than the estimated, but that's okay. And then we get the question, is the design flow rate less than the allowable yield? The answer here is yes, and we get a green check box, which means it's a good check. If the answer were no, that means that the allowable yield is less than what we're suggesting is the flow rate. And what we need to do there is either reduce the flow rate so that it's less than the allowable yield, or we might have to choose a different water source with a higher yield. Next, we get a box where you can explain how the design flow rate was chosen, and then you can explain that here. In step 3B, we're going to be looking at the system layout, and the first question is, what kind of pump is being used? So remember, this design tool is for pumped safe water systems, and so it's not necessarily applicable to gravity-fed systems. But the two options for the pump to be used are the submersible or surface. In this case, we're using a submersible pump. And then we enter two elevations, the dynamic water level and the top of tank elevation. And good to note that these are elevations, not necessarily depths. So you can see those elevations then appear here in the diagram. And you'll notice too that if I switch from submersible to a surface system, the diagram will actually change how it looks. So we can select submersible, and it'll change back to that diagram. Then in step 3C, we're going to calculate total dynamic head, which is equal to static head plus friction loss plus minor loss plus treatment loss. The static head is automatically calculated. It's just the difference between the top of tank elevation and the dynamic water level. And this calculator shows that equation here. And then the only things you have to enter in this step are things about the piped system characteristics. So you'll first define the pipe section and give a description of what that section includes. For example, the pump to the wellhead. And then in parentheses, this engineer has written the description of the pipe, indicating the pipe material. Then you'll define the length for each pipe section, the inner diameter for each pipe section, and it's important to note this is the diameter from wall to wall inside the pipe, so not the nominal diameter, but the inner diameter. And then the roughness coefficient, and finally the minor loss coefficient for each pipe section. You might be wondering to yourself, well, how do I calculate the minor loss coefficient or the roughness coefficient? But you can see when we hover over this cell, we get an explanation about roughness coefficients and what values to use. Water Mission recommends 135 for plastic pipe, but we can see here the design engineer has used 140. So that's just an engineer's choice based on engineering judgment, and that's okay. But then for minor loss coefficients, there's actually this helpful calculator that you can click on to take you to the optional calculators tab to see the sum of minor loss coefficients for a pipe section. We can see here a list of different pipe fittings, and then blue cells where you can enter the quantity of those fittings for each pipe section. So for a given pipe section, the engineer has entered here a quantity of 2 elbows, and then we can see the sum of those minor loss coefficients for that section is 1.6. So you could repeat this for each pipe section, entering the quantity of fittings for that pipe section, and then see what the sum is down here. So we can see that 1.6 appears here in the third pipe section for this system, but then there's other sum of minor loss coefficients that would have been calculated the same way, or could be calculated the same way. Next, we get to treatment loss, where we need to define the number of treatment units in parallel. Sometimes if there's a higher flow rate for your project, you might need multiple treatment units in parallel. If you need to find a way to calculate that or estimate that, you can click on this calculator, this link to the calculator to determine the number of treatment units in parallel. The things to enter here are the design flow rate, and then it automatically calculates the number of LWTSs needed or erosion chlorinators needed if you're using water emission treatment. If you're using other treatment equipment, you could enter the maximum flow rate that's allowable for that individual treatment unit, and then it would automatically calculate the minimum number of other treatment units needed. But in this case, we just need 2 erosion chlorinators. So we enter that number here, and then it automatically calculates the estimated head loss through the erosion chlorinators. If you were using other treatment equipment, you could then enter maybe a calculation that you got from the manufacturer or another specification sheet that estimated the head loss through that other treatment equipment. And then that would all add together to get your total treatment loss. Finally, we add all of these 4 parameters together, the static head, friction loss, minor loss, and treatment loss, to get the total dynamic head. Finally, at the end of step 3, we get a summary of the main outputs from this step. The design flow rate of 7 cubic meters per hour, and the total dynamic head of 100.6 meters. So that's the end of step 3. Thanks so much for tuning in, and I hope you enjoy the next video about pumping.